Good evening and good morning, friends and colleagues. Welcome to our International IVF Alliance monthly webinar. My name is Yifei Liu, and I am the IVF Lab Director at the Penn State Health Hershey Medical Center. Please first let me to thank three colleagues who helped me run the webinar series. So they are Wei Zhang. She is lab manager at Reproductive Partners Fertility Center San Diego, and also Dr. Yu. And she is also famous. She is the program director of the EVMS, and also Dr. Lee. She is a senior embryologist at Sutter Health San Jose. So it is my great pleasure to introduce Emily Muntz, Vice President of the Medical Affairs at Juno Genetics US. She's one of the most respected voices in reproductive genetics today. So Emily has been a certified genetic counselor since 1999. Today, she will bring over 2 decades of experience bridging clinical care and genetics counseling. So she's going to talk today about how to prevent and manage discordant results across IVF lab, PGT lab, and also fetal testing. Please join me in welcoming Emily Muntz. So Emily, please take over from here. Thank you so much.
Thank you so much, Yifei. It's a pleasure to be here. I really appreciate you inviting me today, and I'm excited to speak with all of you. I've watched this webinar series over time, and it seems like you always have interesting topics, so I'm honored to be invited. I'll share my screen, and it seems like there's enough people here that I certainly would be happy to take questions as we go. If there's things you want to ask me, I do tend to talk fast also, so I'll try to slow down a little bit. And then we'll also leave plenty of questions for the end. I also just want to mention that our assistant lab director from Juno Genetics, Dr. Xin Tao, I think is on the call as well. She is very well versed, much more than I am on the technical side of things. She's someone who, has developed the platform that we use at Juno, reviews the results, and helps us with the resolution of the discrepancies that I'll describe every day. So if there are more technical questions, I may ask her to jump in, and I think she's giving this webinar again in a few weeks on a different topic, so that will be great. I'm assuming that you're seeing my full screen, so I will go ahead and get started.
Yes, you're good.
Great. So as you know, I'm a full-time employee of Juno Genetics, and a lot of the examples that I give today are going to pull from the case examples that we've had in our laboratory. I'm sure all of you work with a variety of different PGT labs, and so needless to say, not everything that I say will apply to your lab, but I'll say again and again, one of the themes of this topic is to encourage you to understand exactly how your laboratory manages and prevents discrepancies, so that this topic is directly translational to you. So you already posted the learning objectives, so I'll just skip forward to the outline. What I'm going to talk about today is what are the most common sources of discrepancies in PGT and the frequency of those. And then really I'm going to break the talk down into 2 parts. The first will be how do we in the PGT lab work to prevent discrepancies from ever happening so that you never have to go through a discrepancy that was preventable. And then the second would be when a discrepancy does occur, how do we manage that from the PGT lab side, and how do we collaborate with you in the IVF lab, as well as the IVF clinic and other people who may be involved, certainly the patient, the OB provider, genetic counselors, maternal fetal medicine, to take the case through a thorough root cause analysis and hopefully resolve the discrepancy and be able to provide counseling to the patient at the end of the day. So first, let's talk about what do we define as a discrepancy. So generally, any prenatal or postnatal finding that seems to be inconsistent with the PGT result on the embryo that was transferred. So of course, these could fall into cases that were PGTA cases, PGT-SR, or PGT-M. For PGT-A and SR, this could mean that there's a fetus with a karyotype or pregnancy loss with the karyotype that is discordant from the PGT-A results. Generally, these are going to be these could fall into cases where you're looking at an autosomal discrepancy, but you also could have cases where there's a sex discrepancy. And this could be from a karyotype, but it also could be from something like an ultrasound where we're seeing a different sex. And then increasingly with the use of NIPT in routine prenatal cases, we also, of course, get a lot of calls about seemingly discordant results from an NIPT compared to PGTA. And then there also can be discrepancies with PGTM where there could be a discordant genotype compared to the embryo that was transferred. I'm not going to talk a lot about PGTM today, but I do have a case example I'll share with you about this. And PGT discrepancies, we can, again, kind of divide these up into two general categories, and those would be false positives and false negatives. When there's a false positive, we have an abnormal PGTA result that actually has resulted or could have maybe resulted in a normal fetus or POC or postnatal result. I'm not really going to talk about these today because for the most part, we don't find out about these. So we want to always acknowledge that there is a false positive rate with PGTA, but not many people are ever transferring embryos with positive or abnormal chromosomal results on PGTA. So these, for the most part, go unrecognized. It's the false negatives that are really the focus of this talk and what we all experience in the PGT lab in the clinic. And these are cases where there was a negative or normal PGTA result, but some kind of abnormal result in the fetus, POC, or postnatal. There's not a lot of data on there about how frequently these discrepancies occur. Generally, they seem to occur in less than 1% of all cases, but I think any large PGT lab and any clinic is going to encounter these, on a monthly, if not more frequent basis than that. And there's a lot of different factors that influence how we can, how much we experience this. So first of all, of course, not all embryos are transferred. So a lot of potential discrepancies probably just go unnoticed or unrecognized. And if we have a failed transfer, a biochemical pregnancy, or an SAB, those losses are, of course, not testable. So if there was, for example, a false negative on PGTA that led to, an embryo being transferred that had trisomy 1 and it resulted in a failed transfer or early loss, no one would ever find out that that was the reason for the early loss. We also see, and certainly from the PGT lab side, a really big wide variety in terms of the frequency with which clinics are pursuing POC testing. And, some clinics there's a pregnancy loss and there's not a lot of effort made to understand why that occurred. Other clinics we work with, we are constantly hearing about, the workups that are being done on pregnancy losses, and the tests that are being ordered on those also are widely ranged. So they could be microarrays, FISH, karyotype. Some are doing, whole exome sequencing on pregnancy losses or fetal anomalies. So how often that's done is going to influence how often we hear about discrepancies. And then some people are better about notifying us than others. We have some clinics that are always telling us if there's a discrepancy. Others kind of never think to let us know. Patients also will differ in their uptake of it. So I think when a provider says to a patient, would you like us to do a full workup of this discrepancy and try to understand why this difference occurred? Some patients really want that information. Others are like, I don't think this is going to help me. I just want to move on. Our lab is very willing to work up discrepancies, and we do a lot of this. I have heard that some PGT labs don't like to work up discrepancies or don't have all the technologies available to really fully work them up. So I can't really speak to that, but perhaps that is the case that some labs are not doing discrepancy analysis in terms of what all could be offered. And then, as I already mentioned, there's a lack of follow-up on aneuploid embryos. So these are all things that will influence how well we're really able to understand as a field the frequency with which these occur. So I think one of the things that I just want to acknowledge right off the bat before we kind of get into the weeds of talking about these cases is that we know that there are inconsistencies and differences in how PGTA is done between laboratories. And I'm not going to go into all the different studies, but there are many, many studies now demonstrating that the aneuploidy rates between different PGT labs are different, and that the way things like mosaicism are classified are different, the way that no calls are classified are different. So you can see just on a surface level that there are going to be discrepancies between labs simply because of the different platforms that are used, the different reporting schemes that are used, and how well these different platforms were validated. So I want to first set the stage by just reminding us together that the purpose of PGTA primarily is really just to identify and deselect embryos that have whole chromosome aneuploidy. So this test should not be considered a screening test. It should not be used, I don't think, for ranking embryos for transfer. It really has the goal of identifying embryos that have uniform meiotic aneuploidies throughout the embryo as its primary goal. And so the process of validating a PGTA platform in terms of how well it is able to accomplish this goal is extremely important and something that I think has not been discussed enough in our field. But I'll just mention that the platform that we use at Juno has gone through extensive analytical and clinical validation in terms of transferring actual aneuploid embryos to be sure that the false positive rate of the platform is very, very low. So I'm going to show this slide a couple times as I move through some case examples, and I just wanted to kind of organize our thoughts a little bit first about discrepancies. So I've categorized them in the following way. Some PGT discrepancies are really not technically discrepancies at all. They're really things that fall under the what we can expect in terms of the limitations of PGTA. So we all know that PGTA is not a perfect test. And depending on the platform you're used and the data you're able to quote from that platform and their validation studies, we can say that there's typically a 1% to 2% false positive and false negative rate. We know that there are analytical limitations to the platform in terms of things that we don't even expect to be able to find. And then we also know that there are biological limitations. Primarily, what we mean by that is mosaicism, where, of course, we're not testing the whole embryo or even the inner cell mass that's going on to make the fetus. So we're going to have inherent limitations that are expected from PGTA from the beginning. Another category I would say would be errors. And these can be errors that could happen in the IVF laboratory. These could be errors that could happen in the PGT laboratory or even in the genetics laboratory that's processing the POC or postnatal sample that has a said discrepancy. We also know that in vivo conception is a possibility and of course can cause discrepancies if the patient has a pregnancy that was conceived naturally that wasn't even PGTA tested. And then contamination is another primary source of discrepancy, and I'll talk a lot about contamination and show you some examples today. So going back to the purpose and scope of PGTA and the fact that we're really trying to avoid transferring embryos that have whole chromosome aneuploidy, I just wanted to quickly, again, set these expectations in terms of what we think we should be finding with PGTA and what we can expect to miss. So in terms of full monosomies, trisomies, very, very large deletions and duplications, and certain types of triploidy, all laboratories should have very, very good capabilities to identify these types of abnormalities reliably. When we get down into smaller segmental aneuploidies, XXX triploidy, haploidy, and uniparental disomy, we're going to start to see some differences between platforms in terms of the capabilities. But these should be well understood in terms of the platform's limitations or capabilities of picking these up because they're generally based on technologies and how they work. When we start getting down into very small, like microdeletions and duplications, of course, balanced chromosome rearrangements, and certainly into Mendelian polygenic disease, I'm sure you all know that those are not things that we would expect any PGTA platform to be able to pick up. So again, just focusing on the difference between discrepancies, these would be things where we would have expected the platform to identify this, but it didn't, versus a limitation where the finding that occurred in the discrepancy is actually outside of the stated technical capabilities of the platform. So those are sort of, I don't know that those should be actually categorized as discrepancies because we should really call discrepancies things that we would have expected to find. So if we go back to our list here, I think we could sort of classify these a little bit differently and say, if we have a pregnancy or a fetus with a full monosomy or trisomy, a large segmental aneuploidy, or these forms of triploidy, those are probably considered true discrepancies. These middle ones could be a discrepancy or limitation depending on what the platform was capable of finding. And then all of these on the bottom would be considered limitations. We would never expect to find these on any PGTA platform. Okay, so let's talk about how we prevent discrepancies. I don't think this is discussed very much in PGT, but I can tell you that as a PGT lab, we spend a lot of effort trying to prevent discrepancies from ever happening for things that we are able to identify in the lab at the time of testing. So I'm going to go through some examples of that before I talk about how we manage discrepancies that have already occurred. So the first one is looking at just the quality of the data that we're getting from the biopsy sample. And I think every lab probably has a statistical estimate of variability that they use to judge the quality of the data. The one that we use is called the MAPD, or median absolute percentage difference. I think other labs might use something called an LDR, or log derivative ratio. I think they're generally getting at the same thing, which is the question of what is the level of variability in the data that we're getting from the sample. So if this is a log2 ratio from a next generation sequencing plot where you have all the chromosomes lined up at the bottom and you're seeing 2 copies here, this is a very nice MAPD where we can see that the data points are all hovering quite close together. MAPD is a measurement of statistical variability, similar to a standard deviation. And so we're looking at how far these points are out from the median. Again, here's a sample with a low, very beautiful MAPD coming from a biopsy sample, and here's a sample with a high MAPD where we're starting to get a lot of noise and variability. And this is where it can get risky to make a call on a sample if the MAPD is too high. So for us, we generally will not call things if we're getting up to about a 0.3 or higher level. On our platform, we know that the washing and rinsing of the biopsy is very important to getting a low MAPD. We also know that the total volume in the tube is very important to getting a low MAPD. So we spend a lot of time working with embryology labs explaining that for this platform, these are the things that are the most important, and making sure that that's all dialed in as much as possible to minimize the cases where we have a high MAPD. And we do have benchmarks for each IVF lab where we want to see 90% and 95% of their samples meeting certain benchmarks over time with the MAPDs. So for the next couple things I want to talk about, they're going to relate to SNP genotyping. And so I want to just take a quick minute to talk about how SNP genotyping works, at least on this particular assay that we use at Juno, because this will be important to understanding the next couple examples with regard to preventing discrepancies. So on the platform that we use, which is called PGT-seq, we use actually 2 different technologies, a quantitative technology and a qualitative technology. Both are based on targeted next generation sequencing. So the output you're seeing on the top here is the quantitative output, and this is based on chromosome copy number. I'm sure you're familiar with these plots from looking from other labs. What we're seeing here are, again, the chromosomes lined up 1 through 22, X and Y. And we're looking at the number of copies of each chromosome. 2, here on chromosome 6, we have a trisomy, and on chromosome 16, we have a monosomy. We are running SNPs on every single sample in our lab. We feel that the SNP data is very important to the integrity and accuracy of the test. So this is not an add-on test. This is every single sample is also getting about 5,000 SNPs investigated at the same time. So what you're seeing on the bottom is the SNP output, and I don't have time to go into this in great detail, but very, very basically, we're looking at SNPs, which of course are areas of the genome where people tend to have normal differences. So if someone is an A in a spot, someone else might be a B. And if there's 2 copies of a chromosome, then what we would see here on the SNP output are 3 different lines corresponding to the 3 different genotypes that we could see, and the ratio of those compared to one another. So AA would make 1 line here, AB would make 1 line, and BB would make 1 line. So anytime we see 2 copies here, we should see the 3 lines down in the bottom on the SNP plot. If we see a trisomy, then the SNPs generally are going to back up that call, and we're going to see AAA, AAB, ABB, and BBB. And if there's a monosomy, we're going to see only A's and B's. And so we're going to have absence of heterozygosity. So on a nice clean sample, even if there's a trisomy or monosomy, the SNPs are going to give us a second look at those chromosomes. So now that you know what a normal sample should look like, or at least a good quality sample, even if it's aneuploid, you can see that on this plot, the bottom profile, the SNP profile, has a number of an abnormal B allele frequency, because you're seeing this kind of scattering of the allele frequency plot on the SNPs. this is a red flag that this sample has partial contamination. In other words, it has more than one DNA source that's been mixed together in this plot. And so this is a red flag that what we're seeing up here on the copy number may not be accurate because there are actually two DNA sources mixed together. And it doesn't necessarily tell us right off the bat what the source of the contamination is. Obviously, there are a lot of different types of sources of contamination. In some cases, we can actually do a more complete bioinformatics analysis and narrow down some of these options, particularly maternal versus paternal versus kind of external. But in this case, if it was a one-off, we wouldn't necessarily care where that contamination came from. We just know that the PGT result needs to be flagged as potentially not accurate. So here's an example of a case where an initial biopsy had this pattern of this partial contamination. And you can see here on chromosome 16 that if we were only looking at the copy number, we would have called this potentially a mosaic trisomy 16 because it's a 2.6. However, we know there's contamination here, so we, in our case, would issue a no result for this type of embryo, and the clinic would have the option of doing a rebiopsy. In this case, we did receive a rebiopsy, and the second biopsy showed a normal SNP profile, so that's good. We know that the sample is not contaminated. And what we're seeing on chromosome 16 is a full trisomy. So this is a case where we were able to use the SNPs to identify a case where this was not an accurate result and confirm that the embryo actually was a full trisomy that probably had someone's normal DNA mixed in. Now, this is a case that would have resulted potentially, had the contamination not been picked up, this mosaic trisomy, or sorry, this embryo could have been transferred thinking it was a mosaic. If it didn't make a baby, no one would have known why, but now we know why that would have been because it was actually a full trisomy 16. So we are using SNPs routinely for QC and for error detection and prevention. And so the partial contamination is one example of how we use the SNPs. And another is through the what we call the sibling QC that we do as part of every embryo cohort. So every embryo cohort that comes to us is fingerprinted to examine the degree of genetic relatedness between the embryos or between the biopsy samples that we've received. And so this is a full chip here that we're running. And what you're seeing is all the samples listed down on the x-axis, all the same samples listed on the y-axis. And where the sample crosses itself, you're going to see the dark red square, and that's showing us that that sample is genetically identical to itself, which of course it is. Where you see the orange boxes, those are sibling cohorts, and the yellow is unrelated. So basically everywhere you see one of these larger orange boxes, that's going to be a sibling cohort. And what we use this for is to identify cases where there is something going on with the fingerprinting. So in this case, the fingerprinting is showing that sample E2 and sample E7 are actually identical to one another. And so this could be a case where potentially the same embryo was biopsied twice by an embryologist. And when that happens, we obviously don't know if that result actually, which result that embryo, which embryo that result goes with. And we also don't know where is the biopsy for the other embryo that we now have not tested. So this would be a case where we would not issue a result because one result could be a false positive or a false negative, and the other, we don't know what the other one is. The other situation where this is really helpful is picking up cases where there's a total outlier and an embryo shows that it is not at all siblings to the rest of the cohort. And so this is also important to pick up because there are many different reasons that this could occur. This could be a biopsy from a completely different, family or patient cohort. This could be a mix-up of embryos, or this could be a case of full contamination where we don't see anything abnormal in the SNPs because it's just like a fully normal euploid sample. And so there's nothing to tip us off that that's contaminated except when we do this sibling fingerprinting. So this also would go out as a no result for us so that we could clarify with the embryology lab what the explanation might be and potentially get rebiopsies to try to sort this out. So this is a case that actually, when I was in the clinic, happened to me and my patient. when we were working with Juno at that time. And the first biopsy came back as a normal euploid male. So that was fine. There would have been no red flag of anything on here. However, the fingerprinting showed that this one embryo was not related to the other two in the cohort. So this went out as a no result, although we were told why it was going out with no results. Obviously, it was something that the lab wanted to tip us off to. And we did do a second biopsy, and the second biopsy was a euploid female. And this time it did come back as a full sibling to the other embryos. So that helped us sort out the reason that this, well, it never helped us sort out why this happened or how this happened, but it helped us resolve a discrepancy before it even happened. So if this euploid XY embryo had been transferred without further information, then this family would have been potentially very surprised to find out later that they were actually having a female. And obviously, we appreciated the opportunity to resolve this discrepancy before that embryo was transferred, so that that question didn't come up during the pregnancy as to why is this a female fetus or baby. The other situation that I think we spend a lot of time on in the lab trying to prevent potential discrepancies is being very careful about the types of results that we're willing to issue a diagnostic report for. So this is a situation in which, again, looking at the copy number and the SNPs together, we see that there's a discordance between what we're seeing on the NGS results and what we're seeing on the SNPs. So here you can see on chromosome 3, this is showing clearly as a monosomy, but the SNPs down here are not showing consistency with a monosomy pattern. Similarly, on chromosome 13, we're seeing something that looks close to a trisomy, but down here we're seeing a normal SNP pattern. So this is a case where we would issue a no result because we do not want this to come back later as a discrepancy. And we've actually found that by recognizing these patterns and asking for rebiopsies, about 65% of these embryos come back completely euploid and normal on rebiopsy. So it's sort of a rescue mechanism, but it's also trying to prevent a discrepancy from happening later. Okay, so those are many of the ways that we in the lab are actively working to prevent discrepancies from happening. Obviously, we can't prevent every discrepancy from happening because there are many other mechanisms for discrepancies occurring. So now let's talk about what happens when a discrepancy has already occurred and how do we do a full root cause analysis to try to solve this. So again, with this kind of grid in mind, I will give some case examples that will highlight different cases that we've seen that have fallen into one of these categories. So the first case I'll mention is one where the clinic notified us that they had an embryo with normal male PGTA results, and they transferred that embryo, and the patient unfortunately had a loss. And on the loss, there was a microarray done, and on the microarray, it was found to be a male, but that the male had full monosomy 21. So this is a case where obviously this is a surprise. This is something that we expect to be able to detect by PGTA. We always know there's limitations to PGTA, but this is not something we see very often. So we would, of course, want to work up this case. So the first thing we do is we go back as the lab, we go back to the original data from the PGTA plot. And, we don't necessarily, it's not like we're going to open this and we're going to see, oh, it was monosomy 21. I mean, we've never had that happen, but you still want to just go back and lay your eyes on the data to be sure it was clean, to be sure it was clear. We also go back and look at the sibling QC to make sure that the embryo cohort had passed QC, there was no evidence of contamination or anything like that we could see. And in this case, that all was true. Everything looked good from our side. And I'm sure the IVF lab is also, while we're doing this, they're looking through their records, making sure that they have evidence that the correct embryo was transferred. So we're each kind of digging in to our records. What we try to do in these cases is if the patient and the provider do want to do a full discrepancy workup, then we have the patient sign a release form and we obtain the residual DNA from the POC from the laboratory that did the microarray or whatever genetic study was done. And so we work quite hard to get this DNA from the lab because we like to work these cases up and see how much we can solve from them and learn from them. And so it's in our experience, most patients actually do ask for this full workup to be done once that they learn that it is an option. So we were able in this case to obtain residual DNA from the microarray lab. But what's also, of course, critical to being able to work up these cases is having residual DNA from the original biopsy samples in order to do the full workup that we want to do, which would include fingerprinting. So when we received the DNA from the POC laboratory, the first thing that we do is we actually run that on the PGTA platform. We want to see if we're seeing the same exact thing that the POC lab is doing, understanding that this platform was not created to test POC samples, but we still can test any DNA sample on the PGTA platform. And what we saw in this case was that, so just to remind you, this was a monosomy 21 that was seen in the POC. And so what you can see here when we ran the POC sample on the PGTA platform is that we did see evidence of mosaicism for monosomy 21. So the copy number was not at 1, it was at 1.4. So this is more of a mosaic range or intermediate copy number. So we did not see a full monosomy in agreement with the POC lab, but we did see evidence for monosomy 21, in some form. We also did fingerprinting against the whole cohort of embryos that had already, of course, been run back with the PGT. And it's hard to see here, but this J sample is the, as noted up here, is the POC sample. And it did show that it was an identical match, that's what the I means, to embryo 1, which is the one that the clinic had transferred. So working up a case like this, we're able to say, the correct embryo was transferred, the fetus matches the biopsy from the embryo that was transferred, and kind of relieve the clinic of any questions of, was the right embryo transferred. We're also able to see that while we did see some consistency with the POC result, we did see evidence of mosaicism, which the POC lab had not seen. So we can't really resolve that, but we can at least say that the most likely explanation for this discrepancy in this case is biological mosaicism, which we know is a limitation of PGTA. And this is probably the most common reason for discrepancies that we see in our lab. And I believe other labs have indicated that it is for them too. The second type of discrepancy I'll talk about is analytical capabilities. And I didn't pull case examples for this. There's just too many. A lot of things fall under analytical capabilities as well. One of the ones that we hear a lot about are discrepant from, not necessarily within our lab, but within laboratories that aren't using SNPs to detect all cases of haploidy and XXX triploidy. So haploidy and XXX triploidy, as you may know, look totally normal on an NGS profile. So if you just look at the top of these, they appear to have 2 copies of every chromosome. Of course, the sample doesn't have 2 copies of every chromosome, but because there's no relative copy difference in any one chromosome from another, nothing, the plot is essentially normalized and they look completely like a euploid sample. You need to have SNPs in order to pick these up. So you can clearly see here that the sample has no heterozygosity in the whole sample, so we know right away this is haploid. And for this one, we know right away that it's XXX triploid. We've shown that even in 2PN embryos, about 1% have haploidy or triploidy. If you are not using SNPs, then this is going to be another form of analytical discrepancy that you could experience because you will have patients who have pregnancy losses that are able to be karyotyped or tested after loss, and you will see cases of XXX triploidy that were missed by PGTA because of a known analytical limitation. The other common type of analytical limitation with PGTA comes from the question of resolution. So the resolution of a PGTA is going to be different from platform to platform. We know that, for example, with prenatal testing, there is the ability to go a lot deeper and see smaller copy number variants or changes in the DNA that we are never going to see with PGTA. So, we can think of the karyotype as being kind of the highest resolution, or sorry, lowest resolution prenatal test, then going into microarray, and then of course getting into like sequencing, whole genome and exome sequencing. Those technologies have a high resolution for many different reasons, including they just have more cells to work with. They can culture the cells. They can do more testing than we can do on PGTA. Most PGTA platforms are going to quote a resolution somewhere around 3 to 7 megabases, and we're not going to be able to see small deletions or duplications. So it's not infrequent for us to get a call about a fetus or POC that has a microdeletion or duplication, and it's not surprising that we didn't see that on PGTA. Now, sometimes they're right at the border of resolution. We do, again, try to get that sample from the lab that has it on the fetus, because we still like to run it on our platform and see if it's something we could have seen potentially if we'd had more DNA, or, is it in a region where there's good coverage or not? So we do still like to work up these cases and kind of learn from them. But there's a perfect explanation as to why they weren't picked up. And so again, I don't think of this necessarily as a discrepancy, more of like a limitation. Our group also did a study a couple of years ago where we looked at, we looked together with a clinic at over 6,500 euploid single embryo transfers, and we looked at the most common reason for discrepancies that were experienced in pregnancy losses and fetuses. And there was a mix here of different explanations, but some had tetraploidy, which is very difficult to pick up even with SNPs. Some had deletions and duplications, so those are analytical limitations, but most of the discrepancies were due to mosaicism or biological limitations, as I mentioned earlier. Those tend to be the most common causes. So another interesting case example that we had recently was a case in which a clinic called us and said, okay, we transferred embryo number 7. This was an embryo that had negative, that's the terminology we use for a normal result, a negative or normal PGTA result. It was a female, and this was the one embryo that was transferred in the frozen embryo transfer. The patient had a miscarriage. They had, again, ordered a microarray, and the microarray showed this to be a male with trisomy 16. So in this case, we have not only the autosomal discrepancy, but we also have a sex discrepancy. And I will say that is like a little bit of a bigger red flag, because it's unusual to have one thing discrepant. It'd be very unusual to have two things discrepant, including the sex. So by the time the IVF lab called us about this, they were also, of course, going through all of their records, and they had noticed right away that embryo 8 was actually a male with trisomy 16. So they had gone through all of their data and records, and they told us that based on their review, they couldn't rule out the possibility that there was some sort of sample swap, either at the time of biopsy or at the time of freezing the embryos or at the time of the frozen embryo transfer. So they couldn't be sure, but they were kind of beginning to say it's possible that there is a connection with the fact that embryo number 8 has trisomy 16 and is a male. So in this case, again, we go back to the original plot. We confirm, yes, this was a totally euploid female. And what we do then is, especially for cases like this that seem like they might not be a simple biological limitation, is we start going back through all of our protocol of everything that's been done with this sample. We look at the original paperwork, we look at the chain of custody, and I don't have time to show you all the details, but these are screenshots from the videos that we take when we're processing the samples, which show all the sample numbers. We go back through the raw data and we do a really thorough review of everything. And in this case, everything added up. There was nothing out of line at all here that would suggest anything happened in the PGT lab. We were, though, able to get the DNA from the POC, and we agreed. The sample clearly had trisomy 16 and it was a male. So on the same platform that we used, we were able to say, yes, this is also what we're seeing in this sample. So then what becomes very important is the fingerprinting. So again, going back to the original set of embryos, you may have noticed on that result, there were quite a few embryos in this case. So this is the original PGTA sample cohort that had been the full siblings, as you can see. And then what we're adding in here, and you can see the ID number matches here, we're adding in the POC sample. And if you just go along the line of this POC sample, again, identical to itself here, showing that it's a sibling to all of the embryos. When we get to embryo 8, it is showing that it's identical. So this shows that it's actually embryo 8 that was transferred and resulted in the loss. And as you remember, this is the embryo that was a male with trisomy 16 on the report. So I never heard the complete story from the IVF lab as to what happened with these samples. We ended up doing a lot more work with them on some rebiopsies they wanted to do on some of the samples to try to sort out the whole cohort and making sure that everything was in order in the way that they thought it was to help them kind of continue to resolve the discrepancy for the patient. So this was an example that fell under the IVF lab category in terms of the explanation for the discrepancy. This next case is a case that actually also was mine when I was in clinic, and it was a situation where the patient transferred a euploid female, got pregnant, but on her 16-week ultrasound, she called us at the clinic to say, they're telling me that it's a male. And she really wanted to sort out why this was the case. And so she went ahead and had an amniocentesis. And the amniocentesis confirmed that it was a male of 46XY. And we were able to send DNA from that amniocentesis back to Juno to do a thorough discrepancy analysis. Now, when we have a sex discrepancy, just like any discrepancy, there's many possible explanations. We need to think about errors. We need to think about wrong embryos. We need to think about contamination. Could this have been an in vivo or spontaneous conception? Sex chromosome mosaicism is sort of more of a known phenomenon. So we're always thinking about that with sex chromosome cases. And, as with any case, a technical or analytical error. So with that DNA being sent to the PGT lab, again, they were able to do fingerprinting on the amniocentesis sample and compare that to the residual DNA from the transferred embryo, but also from the rest of the embryo cohort. In this case, we also sent DNA from the parents because the parents just very much wanted this all sorted out. So what we saw from this testing was that the fetus was a full match to the mom and the dad. That gave them a lot of reassurance. They were very worried that this was just a completely wrong embryo that had been transferred. And what the PGT lab could see was that the fetus had a unique DNA fingerprint. It came back as a sibling to all of the embryos that had been tested, but a unique sibling, meaning this embryo, this fetus had never existed in the PGT lab. So this was a case of spontaneous conception. And the patient initially said, there's no chance this happened. I followed all of my instructions around my FET. I was the one asking her about this, so she was very adamant about it. But when we presented her with the data and said, like, this is definitely your embryo, but the only explanation here is a spontaneous conception, she eventually admitted that she had not necessarily followed the instructions given by her clinical care team to refrain from intercourse around the time of the natural cycle FET. So at least we had a good answer for that one. So this is the one, case 3, that fell into the in vivo conception explanation. And this is something that's been described by other groups, other PGT labs. There are published cases of spontaneous conception having occurred where, of course, one of the concerns when that happens is that, especially if it was a PGTA tested embryo, is that that fetus has not undergone any chromosome screening. And that's like usually something that when this is figured out is a concern because we don't know the chromosomal status. And there's even one case report where there was a fetus that actually had 45X and was worked up as a discrepancy. So even though a euploid had been transferred, 45X conception and was proven to be a spontaneous conception. So every clinic does a lot of education on this, but this is really the only thing that we can do to, mitigate the risk of this happening. The last case I'll talk about actually just happened to us within the last week, and it's a PGT-M discrepancy. And PGT-M discrepancies are quite rare because obviously there is probe development and technical approaches to making sure that the PGT lab is able to accurately test for the variants in question. And we don't have as much like situations like mosaicism like we do with chromosomes, where those come up as a possible reason for a discrepancy. But this was a case where we did PGT-M for retinitis pigmentosa, which was in this case an autosomal recessive gene, the EYS gene. There were 3 embryos to test for this clinic, and the middle one here, number 2, was compound heterozygous, which also means affected. So it had the copy, disease allele from both the mother and the father. So that one was essentially not suitable for transfer per the clinic and the patient's wishes. But embryo 1 and embryo 5 were both heterozygous positive for one of the 2 variants. So basically they came back as carriers. We recently received an email from the genetic counselor in the IVF lab saying, you may remember this patient, and she transferred embryo 5. They had a successful live birth, which was great, but they decided to test the baby after birth just to confirm the PGT-M results, expecting, of course, that the results in a genetics diagnostic lab would show that the baby was a carrier. But to everyone's surprise, the child came back completely negative, not even being a carrier for either of the variants that the parents carried. So this then opened up the concern not only about the PGT lab and the accuracy of the testing we're offering. I mean, it wasn't a situation where the baby was affected, thank goodness, and there was that concern, but you still want to make sure that your testing is accurate, even if it doesn't ultimately have a clinical impact. And of course, the patient is also asking, like, was this my embryo if this baby doesn't carry the gene, at all that we thought it carried based on the PGT-M results. So again, we looked through everything. All of the data looked good on our side. We did not see anything out of line that could explain this. And we, fortunately, there was also a pediatric genetic counselor involved who was counseling the family. And we had offered to get DNA to run it ourselves to do the comparisons. But ultimately, when the pediatric genetic counselor went back to the laboratory that did the child's testing and kind of pushed them a little bit to look back at their data, they ultimately ended up concluding after a formal review that they had an error in the testing that was due to allele dropout, making it look as if the baby was negative and not seeing the carrier status. And this is quite unusual. We talk about allele dropout as being a cause of error in PGT because of the tiny samples that we're working with. We don't hear about allele dropout very much when you're able to work with blood samples and larger samples of tissue. So, I mean, this was reassuring because we were able to say, okay, this is not something that happened in our laboratory. And it was nice that it was sorted out. But I think it was just a good reminder for all of us that these can also happen with PGT-M, and that it really takes a thorough review and kind of all parties being involved to solve some of these discrepancies for families. So just wrapping up here with the last couple of slides, putting all this together, I think this is sort of a framework for how you could think about discrepancies when they occur. This is really targeted to more on the clinical or IVF lab side. So you always want to get records of the abnormality to, because the PGT lab is probably going to want to see those. You're then going to want to ask, do we think this is more of a limitation of the platform, or is this like a true discrepancy? If it's a limitation and it's like a tiny micro deletion, or it's something that we wouldn't have expected this platform to pick up, we can kind of set it over here in the limitations category. The patient is going to need counseling to understand why it wasn't picked up, and that was maybe probably reasonable that it wasn't picked up. But that needs to be discussed. If it wasn't due to a limitation, then we're really talking about looking from the embryology side, the PGT laboratory side, and then seeing if there is DNA available on this pregnancy or child or loss that could be used in a full discrepancy analysis. So when we think about both preventing and managing discrepancies, I think there are responsibilities that the clinics have, and then there are, of course, also responsibilities that the PGT labs have. On the IVF clinic side, it's really important to know the lab platform that you're working with for PGT. What do they report and not report? What are the capabilities and limitations of the platform that they're using? What do they do when there's a discrepancy? Do they have a standard practice? Do they have steps that they want to go through? Do they have DNA left over from the embryo biopsies? Because if they don't, then a discrepancy analysis is not going to be possible. It's also the clinic's responsibilities to set expectations for patients. Patients should know PGTA is not perfect. There is an error rate. There are biological and analytical limitations. There are errors that happen. And consent forms should always outline those possibilities. The clinic should have an SOP for investigating these discrepancies. What do you do when you get that phone call? I've seen so many clinics sort of panic and give the patient wrong information or apologize in cases where there ended up being nothing done wrong. We should expect discrepancies to happen and be ready to handle them. And the limitations should also be communicated to any prenatal providers who are involved. So it's not uncommon for clinics to get a call from an OB or a prenatal genetic counselor trying to understand, what could be the explanation for this. And so it's always nice if those expectations are kind of set up front. On the PGT lab side, I think it's really important that labs are transparent with clinics. We share so much data. When we have a discrepancy, we work it up. We give everyone the raw data back. Here's what we saw in the biopsy. Here's what we're seeing on the POC. Here's all the explanations. We're really working as a partner to try to solve these cases together. We don't want to get in a situation where we're blaming each other for anything and not, helping the patient to get the ultimate question answered. We also need to be clear with the clinics we're working with. What is our protocol for storing biopsy DNA? For us, for example, we store DNA routinely out of routine practice. That's in the consent form. Patients can choose to have us not store it, but most allow that. And so we are able to do full discrepancies and fingerprinting in the vast, vast majority of cases. And then we have our own SOP. It's taken us, time to develop that, but now we have a very clear set of steps that we carry out from the moment we get that notification from the clinic that they want us to look into something. Why does any of this matter? I think a lot of this can provide some closure for the patient. They aren't left wondering, is PGT accurate? Was something done wrong by my clinic or by the PGT lab? I think understanding the cause of the discrepancy, if one can be identified, can be really important, especially in cases of a loss where they're trying to understand, is this something that could happen again, or how rare is this? It's also important for lab QC, and I think IVF labs and PGT labs can learn something from discrepancies, and sometimes there's a little thing that will be picked up on a step that maybe could be improved upon from a QC standpoint or a safety standpoint that could prevent this from happening in a future case. It's always an important reminder of the limitations of PGTA for counseling and consenting. And some of these cases will have medical limitations as well, implications. For example, a case where there's a sex discrepancy, but it's due to a disorder of sexual development, and it's something that could be inherited and needs to be tested for, or testing could be offered for a future pregnancy if it's a genetic condition that caused the discrepancy. So with all of that being said, the last thing I'm going to say is give you a shameless plug that at ASRM in just a couple of weeks, I'm working together with 2 other genetic counselors from Baylor and NYU to give a symposium on this same topic. And we'll have some of the same information. And also one of the counselors is an IVF counselor, one is a prenatal genetic counselor. So we'll come together to kind of talk about cases and how we work together to solve them. So if any of you will be at ASRM, a lot of this will be repeated, but there will also be some other cases shared as well. So we'd love to see you there. Thank you so much. And obviously happy to take any questions. Thanks again.